Our next example of the way that the brain systems for space and its systems for memory interact involves synapses. So not only can memory be stored in the activity patterns of neurons, memory can also be stored in changes in the effectiveness of synapses. And of particular relevance for us today, these changes in synaptic efficacy often occur in the sensory and motor pathways that involve processing of spatial information. Evidence in support of this idea comes from a model system involving interactions between our balance sense and our ability to move our eyes. Whenever we move our heads, we tend to counter-rotate our eyes to keep the image of the visual scene stable on the retina. That is, when I turn my head this way, I angle my eyes back to look that direction. When I turn my head this direction, I angle my eyes back to look that direction. Well, I have one more eye movement demonstration to show you. And I have used an important piece of laboratory equipment, namely duct tape, to attach my camera to my bicycle helmet. And this is going to make it easier to see the way my eyes counter-rotate when I turn my head. And I just need to zoom in here and make sure that I've got this centered. Okay, that looks good. Okay, so I'm going to look straight ahead and I'm going to turn my head back and forth, and the image is looking quite stable to me, so that indicates that I am probably counter-rotating my eyes quite accurately. That's called the vestibulo-ocular reflex. In humans and other animals that have quite mobile eyes, image stabilization is accomplished primarily through eye movements with respect to the head. But in animals that have not very mobile eyes but quite mobile necks, image stabilization can happen by holding the head steady as the body moves. A great example of this is the chicken. If you've ever watched a chicken walk, you've noticed that it holds its head steady for as long as possible as its body moves underneath it, and then it snaps its head to a new position and the process starts all over again. So I've got a little video clip of this, and notice how steady the bird's head is as I rotate its body. And you can see the same phenomenon as the chickens are walking around on the ground.
Try moving her back and forth.
You can go that way.
Not like that.
You can go this way.
Sideways. Sideways. She's not.
You can go this way. You can go this way. This way. That's pretty good.
You're rocking her back and forth. Oh, she flew up.
All right. We good?
Yep.
Thank you, Mrs. Honeybunch. Weasley.
That's Weasley. That's Weasley.
This reflex has to be calibrated to be accurate. You need to counter-rotate your eyes in exactly the right amount. So if you're looking at this image right here, that coffee cup, and you turn your head to the side, you need to counter-rotate your eyes by just the right amount to keep that coffee cup centered in the same position on the retina. By matching the eye rotation to the head rotation, the brain can achieve the desired result, which is that there should be no change in the retinal image. The ratio of the desired eye turn to the head turn is called the gain of the VOR, VOR standing for vestibulo-ocular reflex, and it is defined as the amount of the eye turn divided by the amount of the head turn. The desired gain would be 1 if you're looking at something very far away, and that's because the head and the eye actually rotate about different axes, and that matters when something is close, but it doesn't matter as much when things are far away. But the other important factor is whether or not you are wearing glasses. So glasses change the size of the visual scene. And this is a photograph that I took of the New York Times, viewed through the lenses of an old pair of glasses of mine. And you can see how much smaller the newspaper is when viewed through those lenses as compared to when viewed outside of those lenses. So that means whenever you put on a pair of glasses, you have to adjust the gain of your VOR. When you get a new prescription, you have to relearn exactly how much you're going to need to rotate your eyes to keep an image stable on the retina. And researchers have investigated where in the brain these changes occur. How is it that the gain of the VOR is adjusted under these circumstances? And the important thing that has been discovered is that these changes occur within the pathway that senses the head turn and accomplishes the movement of the eyes. In particular, the changes seem to occur in the vestibular nuclei and in the cerebellum. And both of these structures are involved in sensing head turn and in accomplishing eye movements. This is the cerebellum here, and the vestibular nuclei are located inside the brainstem, which is right here. Well, what do we mean when we say that the synapses change in strength? Well, recall that synapses are the junctions between different neurons, and they can vary in how effective they are. You can increase the effectiveness of a synapse by increasing the amount of neurotransmitter that is released, or increasing the number of receptors on the postsynaptic side, just to name a couple of examples. It's not surprising that the VOR gain is accomplished by changes in the strength of synapses, but it is somewhat surprising that the synapses that change are located within the vestibulo-ocular pathway. This suggests that there isn't necessarily a specific area of the brain for storing this information, but instead this information storage is interdigitated with the sensory and motor pathway. That is, space and memory overlap in the brain. In the next video, we'll dive deeper in and talk about a particular brain region, parietal cortex, that has been implicated in both spatial processing and in memory.